Um, okay. So concerning the grid search CV, this is so just a quick overview of what is in the grid search CV. Stuff. I don't. Okay. So the first thing the grid search actually needs is the estimator. It needs the estimator. The estimator now is the model that we actually want to perform the grid search on. And then it takes the parameter grid. The parameter grid are the various parameters we want to adjust during the various parameters we want to adjust where we want to the various parameter values rather we want to make use of when we evaluate the model, the various parameter values. Then the scoring now is the it's just like what we did here, the mode in which we use to check how well the model is performing. So these are the three major values that we need. The end jobs by default, the non-value is still okay for the operation. The CV, we can set that to 5. And then but the first thing I like to do is first define the parameter, the parameter grid. I just like to call it this grid. So the first thing is, since we are making use of the random forest regressor, we want to check the values of the n estimators. That's the number of estimators we should be making use of. The number of estimators we should be making use of. And the thing is, the more the values you input, the longer it takes to find the optimal value. So grid search is a very lengthy operation, which means we'll just be making use of a few values just to ensure that the model doesn't fail for the entire process of the code. Then one thing I like to do is when I'm imputing the values that I'll be making use of in the when performing grid search, I like to look at the scikit-learn documentation for the model. So I would say the scikit-learn.ensemble, which is for the ensemble, then the random forest instead of classifier, I want to make it the random forest regressor. The random forest regressor. So we'll just be looking at the various variables now, the various parameters rather, and their importance. The criterion can actually be an MAE or MSE, but the MSE is actually perfect because, as I said, the MSE uses the maximum value, like the model, it makes use of the maximum value now, the maximum error rather, that the model can generate. So using that maximum error, we are sure that the model has the tendency of actually producing a better value for it. You could always go through the documentation to understand what I'm saying better. But for the video, I'll just make some changes to values like the max depth, which represent the maximum depth of the tree. If not, and then the node are expanded until all the leaves are pure, or until all leaves contain less than mean sample split. So I'll set the max depth, I'll set the mean sample split. Just this two sharp, because what we are trying to do is to just show you how what's the name, the grid search, how grid search works. So it takes integer value, and I'll just take an integer value from the range of say 3 to 5 to give us two values. Let's say 3 to 6, make it slightly bigger. Then we'll do the same thing for the mean sample split. Mean sample split, which will be this mean samples split. That will be the mean samples split. So start from range So, that's very interesting to follow. So this is the parameter grid. It's actually a dictionary of the various values that is a dictionary of the various values that we want to adjust at for the estimator, which is the random forest regressor, to see which one performs best. So we say the grid search CV now. We'll start in the variable grid search. Variable grid search equals grid search CV. The estimator we want to make use of is the random forest regressor. I'll just copy the name of the model. Then the parameter grid is the param grid. It's the second thing I do, but I don't need to make use of the equal sign. So the scoring that I want to make use of is the normal scoring that we've been using all this while, the negative mean absolute error. Negative mean absolute error. That's the negative mean absolute error. Then we also want to check, is there any other thing I need to, okay, yeah, the CV. The CV, that is them for the cross-validation fold. Let's make that start. I think that's all. That's all that we let need for the grid search. So we now say, okay, this grid search now, it has to fit on a model. It will fit on the, I'm not saying that. It will fit on the grid search. Dot fit. It will fit on the training, that's the X train, training data, and the Y train. So use this, we're basically saying use this data to understand the results and look through the various, use this model now, check use the various values now to check which values will best estimate the, which values, if we were to impute into here, would be the best for predicting the value Y of X. So when we say the grid search, it actually takes a while, because if you take a model, say, it creates the model random forest regressor. It places the value 100 here, say maybe place 3, place 2, evaluate it, get the results. Maybe that's the mean absolute score. It just keeps it somewhere. It does the same for 200, 3, 2. It does get the results. Then it says 100, 4, 2, like that. It keeps doing like that till it gets the best performing model. Like it gets all the model performance. Then from all of the model performance with the various different parameters now, it checks, okay, which one performs best. And then that is the result of the one that performs best that we are hoping to get at the end of the training. The reason why I was trying to avoid this process, not because I really wanted to avoid it per se, but it's because it's a time-consuming process. Most of the time, I just like placing all of this stuff in the function as I was trying to describe here. I place it in the function there. I just go do something else and I come back to watch my, view my result when it's done with all of the data processing. But for the sake of clarity, I hope this quickly on so we can all see the results when it's done. And then
while I'm waiting for you to run, let me ask you a question.
Yeah, I'm listening.
Yeah, okay. So why do we perform grid search?
Perform grid search. We're actually performing grid search right now.
Oh?
We're actually performing it right now. In fact, we are just.
I said, why do we perform grid search?
Okay, why? Okay.
Yes.
We perform grid search because of we want to. The purpose of grid search is to like fine-tune the model to check the values of a certain parameter that best fits the model. So we perform grid search to get the hyperparameters necessary for the model. Just like now that we are done with fitting this data into the grid search, we could say something like grid search dot best param which is the best parameter. Now, these are the best parameter values. It's according to our research, it believes that 5 is the best max depth that 5 is the best value for the max depth. 2, which is the default from our documentation here for the mean sample splits, default equals 2, is the best value to make use of. Then the best number of estimator as provided by the this thing, by the key n estimators here is 200. If it's that we have added more, say 150, 250, and the rest, we would have gotten probably a different value. But the thing is, the more the values you place in there, the longer it just take to process it. But once it's done processing it, it will give you something like this. A result of its analysis of the model that actually performed the best and the values that the model, the values of the parameters that perform best. So we can get the model estimator using the grid search dot best estimator. So instead of manually imputing the values into the random forest regressor estimator, just do this. So let's say this, and this gets the estimator for you. And this is the estimator with the values directly placed. The reason why I didn't put this max mean sample split is because by default, that's the value there, 202. So this is what's changed. It's created a new model with number of estimator equals 200 and the max depth equals 5. Now, if we were to evaluate on this model now, I'll just say, you could say something like the final model. That is, if we had done the validation and grid search evaluation on all of the various models, we could just say something like, maybe we realize that this is the best model, the random forest. We say something like the final model equals to this, which is going to be the grid search model. I could say the final model dot fit the X tree and the Y tree. Now, for those that might have questions, like we used the fit on the grid search.
We have used it before.
And now we are making use of it on the fit model. The thing is, when we made use of it on the grid search, what it did is that it used it to, it fitted the model. Immediately it was done getting the performance of the model, it deleted the model and it kept the parameter value of each model that is necessary. So at the end, what the grid search gives us is nothing but results. It doesn't give us a model. This model that we get here from the grid search, the best estimator, that is the best performing estimator that I gave us, is a new model with the parameters and these values set in that model. And that is just all. So we now need to refit this model that was given as the best performing model. We need to refit it to get the to train. We need to retrain that particular model now. That's why we perform the fit on it. So there's a question here. It said, since grid search is giving us the best hyperparameters, how come submission metrics varies? Should we be getting the same model? Or shouldn't we be getting the same model, which is the best with the same metrics? I don't really understand the concept of submission metrics actually. They said, how come? Okay, submission metrics. So does it mean the final evaluation? Sorry, could you like rephrase the question? I don't really get it. So just to forge ahead, the final model, this being the final model now, we would have to evaluate the model now, making use of the predict. So say the predictions rather of the model will be that final model dot predict, the final model dot predict, so, predict the x underscore test. So this is going to be the prediction. Now we want to ask for the mean in absolute error of the true value now, which is going to be y underscore test, and then the prediction is that. So we see that we have a score of 717, which is, I think, lower than the other one we had when we I was 788. So there is something else. So I think so. Okay, it said submission at completion. So since grid search is giving us the hyperparameter, and since grid search is giving us the best hyperparameter, how come submission, the submission at competition varies? Shouldn't we be getting the same model, which is the best with the same metrics? Well, the truth is, the reason why we're getting this is going to always vary. The reason is that, imagine we had, someone said something on the group yesterday after we were done with the class. He said, I thought future scaling was for the old model. Now, the thing is, if you perform future scaling on all of these data here, this numeric data, it will actually change this outcome. It will actually change this outcome here. The value might be higher, it might be lower based on the pattern the model took. And aside from that, if, let me say I added something, my number of estimators started from values like between 5 to 1,000. Someone else could do something that is lesser or even more. Now, the reason why the submission will never be the same is because we will never actually follow the same process to attain the outcome. What I did here isn't actually the best result you could get. If you were, say, when we worked from the very start of this notebook, we were to like drop the columns, we were to like drop these columns that we had issues with. That's the item weight. Yeah, we had issues with the item weight, and we had issues with this. If we were to drop the columns, the result might actually be better because now there will be no specific column that is predicting wrongly on the new data. I don't know if you get my point. Your approach to solving the problem is what caused the variation in the output, the performance of the model at the end. That is why data cleaning is very essential, because the more accurate our data is in the data set, the more accurate the final result will be. And once we know more about the values that are here, for instance, this item identifier, but just let me just transpose out one big secret, is one of the major reasons why we are actually having such a poor listing generalization. The reason is that from here now, that's trying to preview the listing. The item identifier really doesn't have any real order. The FDA 15 now, we didn't bother like researching on what it represents. We didn't bother checking whether this DRC meant something or whether there's actually a order that exists between this. We just made use of label encoding, which practically guessed what the order should be. Now, this guessing of the order can actually have meaning to what the final outcome should be. But because our model is actually guessing it, the flaw of the machine learning model is going to be exposed, because the machine learning model, not knowing what the impact of this value here means, it just applied it directly in its learning process. So when applying it directly, it starts getting errors, like it starts failing, because the value 156 might actually supposed to have been, say, 200. Okay, it might actually have supposed to have been 200, whereas we asked it to be 156. Now that little change, so to say, would actually cause a huge rift, because it's just like asking a model to classify between a cat and a dog, and you actually carry the picture of a rabbit in place of the cat. Now, the model will learn irrespective of the fact that you made mistake with the values you provided to it. But it doesn't stop the fact that the model is actually making a mistake. It's not actually learning the stuff properly. That's why the data cleaning process during machine learning tasks is an extremely essential process. You try to ensure that when you encode, you are putting the right values there. When you try to fill missing values, you try to see to it that the values that you are imputing are as accurate as possible. Not necessarily 100%, but you just try to get something close enough to the truth value. And by the time if it's that we have done all of this stuff properly, we would have gotten a better would have gotten a better result. So there will always be variation based on how accurate the data is, based on how well the future scaling was applied, and all of this stuff, all this small stuff that we were just talking about, they all play an important role in getting to this final stage. So what I'm just trying to do is like give you guys an overview. If we were to work on a real this thing, it would take weeks, maybe not necessarily weeks, maybe weeks is just an exaggeration, but will definitely take time, especially with the data cleaning process.
So I want to ask a question.
So yeah, I'm listening.
Please, what is hyperparameter tuning? Like, what is it all about?
Hyperparameter tuning is exactly what we did with the grid search. Right?
Okay, grid search. Okay.
Yeah, it's exactly what we did with the grid search, where we tried to check the various parameters, tweak them to see which parameter best suits the model. That's just it. So once we be able to do this, after like let's say, because from what we did here, what we did here is just like a summary of this whole notebook. But at the end here, I did something where we got the best performing model from our notebook here was the random forest regressor, which had about 775 for the listing for the grids from the grid search, and 784 from the cross validation score. Now we could move further with just making use of that model in our fine tuning. That's fine tuning only the we could move further by fine tuning only the random forest listing, and we could add the random forest regressor model to another model in a process called a voting regressor model. And a voting regressor model is nothing but you carrying two good models that perform pretty well. That's two CPT models that perform pretty well and combining them. And that's part of the activities from the notebook. So after this class, I just want you guys to try your best to be based on what we've done in this notebook. Try to practicalize, try to follow up the activities. If I was to like even create another class tomorrow and the next, we won't actually be done with this stuff. So one of the best ways that I've learned to thrive in the world of programming is to practice and practice and practice again. To always ask questions, always Google things out, always try to find out the reason why this is working the way it does. And you do a lot of reading as you go on with the tasks. But one thing, like this is the thing I want to point out. After getting the best performing model, which is this now, this was what we get as our big math predictor, which is the random forest regressor. The fine-tuning process is also a grid search process, but it's going to be unlike what we did from the start. We just looked for like little values. It's going to take more extensive parameters now, but not just the parameters. You have to have an intuition of what each parameter does. So I talked about the random forest regressor a bit. Then I stated the function of the various hyperparameters now in the hyperparameters in the random forest regressor, and why we elected the ones we picked, and the values, the reason why we picked the values we picked as well. And at the ending, we got the best parameters to be this. So when we applied that, this was the best estimator. We still studied in the variable big math predictor. That is, we called this to be the variable that will be the estimator now for our final project. And after training and making our final prediction, we got an MAE of 753, which is kind of lower than most of what we've been doing. Now, this is the final process.
Question.
Yeah.
In this line 70, you said big math predictor dot predict x var instead of, it's not say s test. Why do you use x var?
The X var stands for the validation set. You know, this is the training set, this is the validation set, this is the practical exam that we're talking about. So we're asking how well it performed on the practical exam.
Hello.
Yeah, hello.
Hello, good evening. Yes, I have a question too. So my question goes to us. Mr. Mohammed, that was the previous
instructor. Yeah.
Actually mentioned that in he actually mentioned, he said they have to give problems like with data sets to use, like in performing some data set to work on. So he said that they are going to give certain amount of data, a certain percentage of data, let's say 70%, for example, or 80% of the data to candidates. Why they keep about 20%? That is 20% of the test data. Why they give 70% of the trained data for students to work on. So whereas from the trained data, the candidates are being given. So they will have to also split the data into their own test and trained data they are going to work on. So, like, can you please shed more light on that? And also, this validation test, train test, and also the validation test, train test, and test test. I mentioned here also, like, I don't really understand the validation set particularly.
Okay, this is what I'll just say. I'll just try to make it. I've been making of this practical example, and I'll just repeat it again. When you when you're in class now, when you're in the class, the course that you're actually taking now, when the lecturer is actually, for instance, in a math class, the lecturer actually shows you the question, the lecturer solves the question, and the lecturer tells you the answer. Now, the process of the lecturer showing you the question, solving it, and telling you the answer is the process of training you. That is where you're actually learning the mathematical problem. Now, that process, the data that we use for this process is what we call the X train. That is the training data, the X train and the Y train. Now, before, in a semester now, there are often like 3 CAs, that is 3 practical tests before you go to your final exam. Now, that practical test, what it does is that it's not actually the main test, and it's not always as huge as the major test that you'll be doing at the end of the semester. But the practical test tries to test your knowledge of what you've been doing in class. So after you have your first CA, you are graded on your performance. Then you go take the class again. Then you are graded. That is with the second CA. You take the class again. You are graded with the third CA. Now, those process of you training and coming back to to perform evaluation on what you've learned over and over again is using the validation set. Now, notice I didn't call it the test set, but you're making use of the validation set. The validation set is ensuring that you actually understand the process well enough. Now, there's a level that you take a test to that you actually understand the course well. Now, the exam is now going to be the final proof of what you've been doing in the class. It will test your knowledge from both the classes and the practical tests. That is where the test set actually comes in. So I don't know if that example that I gave breaks down what the training, the testing, and the validation is all about.
Yeah, it does. It does to an extent.
Okay. So like what I was saying, this is our final predictor. After evaluating now on the test set, what we do at the ending is that it combines the training and the validation sets now to train the final model. Now, this is the important thing. As I was saying from our example, when you are before you write the exam, both what you take the exam that you took in your the classes from the courses from the class and the tests, that is the practical test that you did. All of this stuff combines to see how well you will do on the exam sheet, which you've never seen an exam question before. But if you see an exam question, most likely you prepare the exam yourself. But the goal of an exam question is that the questions that will be asked at the end is something pertaining what you were taught in class that you've never been asked before. It tries to see your ability to generalize to new information. So that is just the process. Now we create maybe X-train is a bad way of naming it. Maybe we should call it X-pod. If we call this X-pod. Yeah.
Sorry. Can we refer to the validation set as also the test set?
Yeah, the validation set is, you can't refer to it as the test set, because if you refer to it as a test set, will actually cause confusion. The validation set is actually testing the training sets, but it's not doing the final testing of the training sets.
Okay.
Yeah, it's testing it, but it's only testing it during the process of model selection. But when you are done with selecting the model and everything, and you've made your conclusion of, okay, this is the model we'll be making use of, then you go and make your final prediction on the validation, on the test sets. That's why they had to distinguish between, most of the time, the validation set is also called the dev set, that is DEV, short for development sets. So when you are developing the reasons why you select a model, you make use of the validation sets. So after doing that, we'll combine the X-train and the validation sets to create an overall conclusion of what the training data, the new training data will be. So after that, what we do is we now train the new model on the what you've been doing throughout the whole session. That is what we've been doing in the whole bulk of the whole class. That is beginning from this session upward. We now train it, and the final model takes what we have learned from both the training and the validation. It combines what we've learned from both of those stuff, and it creates a new model that I've learned from both the training and the validation, and it now tests on the test sets. Now that test set that we dropped for a long time that we didn't even peep at it is now reviewed at the ending. Yeah, and after making prediction on that, we see that our MAE further drops from 753, which was what we called the best, at least as of that time, to 728 as the final evaluation. Okay, we use the validation data sets to find the best model, which we will now apply on our test set. Exactly, that is just what I've been explaining. So thanks for the clarification here. So that's really all for this class, for the regression class. Normally, we were supposed to have talked about the pipelines.
I have a question.
Okay.
You didn't teach us about this SG boost. I think I saw something like an SG boost or something.
Yeah.
You didn't say anything about it.
I made use of it in the examples. XG boost. XG boost is like they call it gradient boosting now. Gradient boosting. It's like an advanced way of actually making use of a regressor, the random forest regressor. It performs the exact same function as random forest regressor. It's just that it has more parameter compared to the random forest regressor and can actually do more. It is a more robust estimator. There's a more robust model now. And the reason why I didn't really talk about it that much is because I just wanted you guys to have an overview that it exists. Because if you notice, when we imported the XGBoost, we didn't import it from scikit-learn. I'm just trying to scroll to the place where it is now. If you notice, we imported it from XGBoost, which is like a framework of its own. And when we started with the course, we were like, we'll talk more about scikit-learn and scikit-learn alone. So the reason why I skipped it is that if we were to talk about it, you can actually configure the XGBoost directly in a pipeline because it wasn't built under scikit-learn. But it is more powerful than the random forest regressor, as I stated at the end of this thing. I would really encourage you guys to take your time to learn it on your own, and if probably time permits.
Sorry, let me ask something.
Okay.
So the XGBoost regressor is an algorithm on its own.
It's an algorithm,
just like
yes.
Linear regression,
Exactly.
support vector.
In fact, it's more like the random forest regressor. It's just a lot more powerful than it.
Okay.
Yeah, it's a lot more powerful than the. With the XGBoost, we can actually get an error MAE of as low as 500 if we fine-tune it properly. But since I don't want us to, because if we were to jump into that one, it will bring more complications into the subject, and it's already complicated with the way that it is right now. So I said we'll just keep that for now. We'll just keep the XGBoost. We'll work with the one that is simple enough for us to work with. That's the random forest regressor, which also performs quite well. So that's that will conclude the class. Actually, we should have done things like the pipeline and making use of pipelines and column transformers and all of this stuff. But I intentionally left that because we still have another class to take on the classification. What we just did now was building the models on the regression. So when we go to the classification, I might not really be talking about all of these steps of creating a function that will automatically perform the grid search and all of this stuff. We might just quickly create a function that does all that, and we want to really learn how to create a pipeline to perform the major tasks in the data modeling overall. We just create a pipeline that does the data cleaning, feature engineering, all the way to the prediction. That will be in the classification set. So I want to thank you guys for the session today, and I hope you guys learned something from it.
Yes, there's one last thing.
Okay.
Yeah, I know I was going through the notebook, but I didn't understand what you did in line 14. I don't know if you can just go to line 14, and just explain what you did there.
Line 14. Okay. Oh yeah. Yeah, I updated that here too. I just realized that the code there might be hard to understand.
So what complex, like when I could not understand it.
The funny
like
thing
13 and 14. I was cracking my brain. I could not understand.
Sorry, it's actually my fault. I was writing the code as though I was writing to myself. I forgot that I was actually it was supposed to be a tutorial note. Basically, to understand what is happening in the code, you need to first start with here. What does this particular code does is the Big Mac sales outcome the unique value for the outlet identifier. So the outlet identifier represents this. So we get the unique values for all of them. So what I was trying to do is I wanted to encode these values by the number 49184910 like that. So instead of making use of a encoder to do that, I just wanted to get that these values 4918 are more accurate compared to if a label encoder data. So what I just did was I just created a short code that does that encoding directly. It was something that I did. I was listening to a music